Good afternoon and welcome to our seminar, Microwave-Assisted Chemistry in the Classroom. I'm your moderator, Michelle, and Grace Vanier, Product Manager for CEM's Life Science Division, will be our presenter today. Grace heads a team of chemists and engineers in the R&D of new methods and instrumentation for chemical synthesis and bioscience applications. There will be a Q&A session at the end of the seminar, so please feel free to send in your questions via the question panel at any time during the presentation. Thank you for joining us today, Grace.
Thank you, Michelle, for the kind introduction, and I'd like to welcome everyone to our webinar. What I want to talk to you about today is how you can use microwave technology in your classroom in a teaching setting to be able to incorporate that into your curriculum. So just to start off, I'm going to talk a little bit about what are the benefits of microwave technology. Why would somebody want to use this technology? Why is it something that you should think about incorporating into your curriculum and teach about to your undergraduates? And for several reasons, and the first three here, I'm going to kind of pop them up quick. These are some of the things you'll normally hear about when people talk about the benefits of microwave for chemistry, and that it's at faster reactions, higher yields, and improved purity. These are the three big things you hear people talk about, and oftentimes they kind of go hand in hand. Because you can do reactions faster with the microwave, you often cut down on side reactions, which will then improve your purity and therefore your yields. And these are all pretty well known, pretty well documented, so I don't want to spend a lot of time about that. But I did want to just spend a few moments to talk about some of the disruptive characteristics of microwave technology and what makes microwave energy a unique source of energy as compared to conventional heating. And some of these characteristics are listed here. So first would be rapid energy transfer. So basically you can turn on the microwave and there's energy immediately being applied to your sample. And your sample will begin to immediately absorb that energy. And it could be your solvent or your actual substrates, your catalyst, something like that. And it's an instant on and instant off energy. And what I mean by that is once you turn the microwave off, there's no more energy being applied to your sample. And so you could take advantage of that. You can do, say, pulses of microwave energy. So turn it on for a few seconds, and then it can be off for a few seconds. And this can actually have some interesting effects on your chemistry and on your reactions. Typically, it's a large amount of energy that we can apply with a microwave. The systems that I'll talk to you about today can do up to 1,800 watts of power being delivered to your samples. And it can be selectively directed. Now, what I mean by this is that you can actually select your conditions, say your solvent, for example, to allow the maximum amount of microwave energy to be applied to your sample. So say, for example, you want to get most energy to get to your actual reaction mixture. You might choose a solvent that is low absorbing or maybe a medium absorbing solvent in the microwave. But say you want to get to a very high temperature and you want to get there very quickly, you might choose a high absorbing solvent. So again, you can selectively tune the conditions at which you're running your chemistry. So I just briefly wanted to talk about annual publications that cite using microwave-assisted synthesis. And so this is just over the past decade showing you basically the number of publications. And you can see that over the past 10 years, it's gone from about 1,000 publications to approaching 4,000 publications per year. And again, these are papers that explicitly state that they're doing microwave-assisted chemistry. So you can tell that there's quite a bit of use of this technology, and it continues to increase over time. And this is important, and how this ties in is why would you want to teach about the microwave technology, and why would you want to teach your students? As we can tell from that previous slide is there's a wide industrial acceptance. There's a lot of people out there using this technology. And of course, publications are by industry and of course by members of academia. But bottom line is it's an essential technique that many, many people are using. And so this is important for you to prepare your students to be our future chemists, either in industry or in academia. They need to know about this since it's a technique that's so widely used. And it gives your students an opportunity to do chemistry that they may not be able to do in a classical laboratory setting. For example, there might be a reaction that normally under conventional techniques takes maybe 16 hours to run. That's not something that you could do conveniently in your teaching lab. So students won't get the opportunity to actually do hands-on or with hands-on be able to run that chemistry, and they can only really learn about it on paper. But the microwave opens up the opportunity to run that reaction because it may only take about 10 minutes in the microwave system. It also gives you the opportunity to have potential for greener reactions. So there's many different ways you can approach this, and kind of all combined too. You can look at trying to use less solvent, or perhaps change your solvent from something that's harsh to something that's a little bit more green. You can choose to go completely neat, so no solvent at all, and that's actually, there are lots of examples where that works well. You can reduce the amount of catalyst that's being used. If you improve the efficiency of the reactions, you can cut down on perhaps the excess. Many, many different ways that you can use the microwave technology for greening your reactions. And lastly, students are excited about new technology. Now certainly microwave technology has been around for quite some time. We've been using microwaves in our kitchens for many, many years. But using it in the laboratory is still kind of new, and it's more of a high-tech technique than, say, using just a classic hot plate or a heating mantle to do your heating of a reaction. And students they like technology. And so that's something that you get here with the microwave systems. So what do students say, though, about using the microwaves in the laboratory? So there are a couple of labs that have already been using the microwave techniques, and so I just wanted to pull a couple of actual student statements and talk about that. So in one example, the students said that they were excited to know they're learning a technique that's just being introduced to industry and something that they define as being used in the real world. And of course, if the students can relate to a technology and realize that it's something that chemists are using on a day-to-day basis, they might be more interested in that. And that's certainly true with microwave technology. And then also they say they can do a number of syntheses in the same time it takes to do a single synthesis. Now certainly we all know students can make mistakes in the laboratory. And unfortunately, with traditional methods, students that make a mistake often just have to learn, okay, well, next time I run my reaction, I need to remember to read my instructions more carefully, don't add too much solvent, whatever it might be. Well, with the microwave, because these reactions are often 5 or 10 minutes long, student can actually go back, rerun the experiment in the current laboratory time, and be able to see with the adjustments made to their methods that they actually get the products of interest. And so this is something that really is appealing to students because they can actually learn from their mistakes and see in real time fixing those problems instead of having perhaps to come back during another lab session and rerun the whole experiment. So what are some of the other advantages of using microwaves in your teaching lab? Well, certainly you get the advantage of faster laboratory procedures. And what this means is that you get less idle time for your students. So I show here a nice little cartoon of a cell phone. So your students don't have this time to be able to be on their cell phones and updating whatever social media site that they're currently using, seeing what's going on with their friends, saying, hey, this stinks, I'm in lab right now, because they don't have that. They only will run a reaction for maybe 5 or 10 minutes. And what this gives you as a professor is more time to lecture. So perhaps it gives you more time in pre-lab to lecture about what they're going to be doing, or perhaps while it's running, in that 5-10 minutes, you can maybe give them a little bit more information about the actual chemistry, or perhaps some time at the end of the lab and teach them more about the workup or the analysis that they're going to be doing. I've already mentioned the fact that you can run greener reactions, so certainly more efficient reactions can be done. With the improvement in yields, you can get better atom economy in terms of not having to use huge excesses in these particular reactions. And because you don't have to use the hot plates and the condensers and things like that, you actually can reduce the energy requirements that you need for the lab. And lastly, they're safer than your conventional techniques. What do I mean by that? Is that you don't have to worry about having open flames, Bunsen burners in the lab, and you also don't need to have oil baths that students can potentially burn themselves on. And I mentioned before the fact that you could actually switch from more toxic solvents to something that's less toxic and less hazardous for the students to be exposed to. Again, it improves the safety for the students. So just want to take a few seconds to talk about microwave theory, just to make sure we're all on the same page here, and I'll tie in basically to the rest of the presentation. So here I have a schematic of a microwave. So you've got a perpendicular electric and magnetic field, and this is moving at the speed of light. Now it's this electric field that is actually going to interact with your sample. The magnetic field, by and large, does not partake any of the heating mechanism. The frequency that we operate at with our systems, and also the same as your home microwave, is 2450 megahertz. And again, that's largely because of the FCC. There's actually only certain frequencies that we can operate under which, and of course, because your home microwave uses the same frequency, the magnetron technology is pretty well known and pretty well established, and so it's a way for us to cut down some cost in the system. So there are two different mechanisms by which microwave energy heats a sample. Now these two mechanisms are called dipole rotation and ionic conduction. So what I have here is a little cartoon movie of dipole rotation. So what you see here, we have water molecules in our sample, and then this here is our electric field of our microwave. Now as we know, water molecules have a dipole moment. So what's going to happen, as this electric field passes into our sample, our water molecules will begin to align themselves with this passing electric field. Now, what will happen is it'll try to align itself, and then another microwave will come through every nanosecond, essentially disrupting the current progress that the water molecule is making, and then again begin to align itself with that new microwave field. And so it's always constantly trying to align itself, never perfectly following that electric field. And what happens then is this basically induces this motion that you see here, this wobble effect, and that kinetic energy then gets translated into heat. Now ionic conduction that I mentioned is very similar. So you can imagine that instead of having these water molecules in solution, you actually have ions that are moving, trying to align themselves with that passing electric field. All right, so that was more of a microscopic view of what's happening when you're looking at heating with microwave. But let's look at more of a kind of a macroscopic view and actually compare microwave heating to thermal or conventional heating. So conventional heating relies on conductive heat. So I have a little over here just a drawing of what I mean by that. With conductive heating, what you have to do is you have to heat up the surface. So this might be your heating mantle, a hot plate, the oil bath itself, whichever one of those. That has to heat up first. Then that energy, that heat, has to transfer to the outside of your vessel, and then the heat then transfers to the inside of the vessel and then slowly dissipates through your sample. Now this is a slow process. It takes time to heat up your sample. It takes time for it to actually reach your ideal temperature. And then once you've turned off that hot plate or that heating mantle, it's still hot to the touch. So you have to be careful, because if you were to leave your sample there and it's sitting there still on this hot plate, you could be causing things like decomposition to take place because it is still hot. There's still energy being applied. Now microwave energy is very different. So here I have a drawing of what's happening with microwave heating. So here we have our vessel, and this is transparent to the microwave energy. So instead of heating the outside of the vessel, the microwave energy will pass through the vessel wall and into the sample and directly interact with your sample, be it your solvent or your substrates or catalyst or whatever it is that you have in your reaction. And so what will happen is each of those different components will begin to absorb that microwave energy, resulting in essentially volumetric heating of your sample. So all the samples being heated at the same rate. What this does is results in a gradient where it's going to be much hotter toward the center of the sample, and it's going to be a little bit cooler than toward the edges. Now the converse to that is conventional heating, which I showed you before, is going to be much hotter toward the outside and cooler toward the center. Now you'll see here I have these red dots kind of illuminating as we're heating the sample. And what this is kind of trying to show you and to represent is this idea of localized superheating. So if we're running, for example, a transition metal catalyzed reaction, and we have say a palladium catalyst in there. That palladium metal we know will absorb the microwave energy, and what will happen is it'll absorb that energy and it'll heat up very, very quickly. And that heat that is generated will be rapidly dissipated by all the solvent that's surrounding it. So what will happen is you don't end up seeing that high temperature of that palladium, but you can imagine that due to that microwave energy that the palladium center itself is probably much hotter than the actual bulk temperature, the measured temperature. And that's what we mean by localized superheating. You might have these what we call microscopic hot spots in the sample, and this is actually what's helping to accelerate your chemistry and speed this up. Now, of course, when you turn off the microwave, there's no more energy being applied, so no more microwaves passing into the sample, so no more heat being applied, and therefore the reaction will then just have to cool down. So again, I mentioned that instant on, instant off. As soon as you turn it off, there's no more microwave energy being applied to your sample. All right, so you might be wondering to yourself, okay, well, this is great. Microwaves heat things up fast. They make reactions happen quickly, higher purity, lower side products, things like that. But you might want to know, well, why would I want to use a scientific microwave system when I could go down the road and get something for much less money? And there's a couple of really important reasons. The first of which is reproducibility. Now, scientific microwave systems provide a lot of control. There is control for temperature, so either via a fiber optic temperature probe or using an external infrared temperature sensor. The pressure can be monitored and the power can be controlled. You can control the power down to perhaps even 1 watt of power if that's what you choose to control. Domestic or conventional microwave system won't have any of that control. And so you won't be able to control exactly how much power is going into the sample. You certainly won't be able to measure your temperature or the pressure inside the vessel. In addition to that, the systems have specially tuned cavities specifically for the types of materials that you're trying to heat. That makes a big difference in terms of the microwaves being able to heat the samples you're looking for. The systems also feature electromagnetic stirring. So while the microwaves do heat the samples volumetrically, it is important to stir them, especially if you have a heterogeneous reaction that you're trying to heat up. So reproducibility is one of your key important things, but probably even more so important is safety. Of course, in the laboratories, teaching laboratories, safety is of the utmost importance. And these scientific microwave systems are designed with safety in mind. So they've been tested for leakage, for microwave leakage, and they're verified that they're well below the limits of what you can have for microwave leakage. They're resistant to the chemicals. Many of the chemistries I'll show you today are organic chemistry based. So they're not as harsh of chemicals, but in some examples, some of the chemistries involve very harsh chemicals, harsh acid reagents, for example. And these systems are actually designed to withstand that and avoid corrosion. And lastly, they're designed to withstand any sort of explosion inside the cavity. Now, of course, we certainly don't want any of that to happen, but we understand that students can make mistakes again, and so in the event that a student, say, adds twice as much catalyst or 3 times as much, 10 times as much, if something were to happen inside the vessel, the system is well designed to handle that kind of event happening inside the cavity. All right, so some of the tools that you have available for teaching with a microwave system are available from CEM. Our Mars 6TA system. So I have it pictured here, and this is actually shown right now in what we call our open vessel configuration. So each of our systems can actually allow you to run with a round bottom flask. This would be a standard flask that you would have in your laboratory, and with a reflux condenser. And this allows you to run a large batch reaction, especially in this particular case, large reaction at reflux. So, but it also can run sealed vessels in a parallel format. And so with the Mars 6 system was what we call our parallel microwave synthesis unit. And I'll tell you more about the parallel nature in a second. Just let me tell you some about the features of the system. So it does feature reagent stirring. So there's actually stirring, so you can stick just standard stir bars inside the vessels for stirring. There's fiber optic temperature control. So this is an internal direct temperature measurement. So you know exactly what the temperature is inside your reaction mixture. There is an I/O port situated in the top of the cavity. That's actually how this condenser is coming out of the top of the system, which allows you to run these atmospheric reactions at reflux using your standard laboratory glassware. And also you can run pressurized reactions in parallel, or what we would define as rigorous conditions. So that means above the boiling point of the solvent, so higher temperature, higher pressure. And so to run those parallel reactions, what we prefer to use is our GlassChem teaching vessels. So here's just a picture of the turntable. So you can see there's 24 reaction vessels here around the turntable. And so each one of these is an individual vessel. And I'll show you the vessels themselves. So here's the design. They're a very simple, very easy to use vessel. So it's a glass mill, 20 mil glass vessel with just a plug and a cap. So very simple to assemble. Just put the cap the plug into the vessel and then screw down the cap. Now you can see here I show a stir bar because again we do recommend stirring inside each of the reaction vessels. Now you'll notice here on the turntable one of these caps is a little bit different, and that's because this is our control vessel. The control vessel features a thermal well, so that's what this is held in place by this brown plug here. The thermal well protects the fiber optic probe. But again, you know, the rest of the vessel assembly is very similar with the plug and the cap. So what these GlassChem vessels allow you to do is run up to 24 vessels, as I mentioned, at a single time inside the cavity. And the temperature and pressure limitations are 180 degrees Celsius, and the maximum pressure in the vessels is 200 psi. All right, so perhaps though parallel synthesis is not the right tool for you. So we also feature our Discover SP system. So again, I have it shown here and showing it in our open vessel configuration, but you can imagine that this piece right here, this is actually our pressure device. So if we didn't have the open vessel condenser, this can come forward and close down on the vessel to run pressurized. So this is a sequential microwave synthesis unit. Sequential because it can only run one sample at a time. So very similar to the Mars system, it features reagent stirring. And now this system uses infrared or IR temperature control. So how that works is the temperature sensor is actually situated in the bottom of the cavity, and it's going to measure the temperature from the outside of the vessel from looking at the bottom of that vessel. Now we can run those vessels up to, that system up to 300 degrees Celsius, and it has a simple attenuator design. So attenuator is what we call our microwave door. So this piece right here, this silver piece, this is what allows us to run the atmospheric reactions. But you simply have to just do a quarter turn to remove that attenuator and then put the appropriate attenuator in place for running pressurized reactions. And again, in that case then, the pressure device would come out and close on top of the vessel. The pressure device allows you to run reactions up to 435 psi or 30 bar, depending on the particular vessel you're using. And it's a focused microwave cavity, so it's a small microwave cavity. And to give you an idea on size, the cavity itself is about the size of a coffee cup. And again, this is what allows us to very efficiently heat our samples and very quickly get us up to temperature. Now the vessels the system can handle, as I mentioned, with your standard laboratory glassware to run it in an open vessel, up to 125 ml round bottom flask, and then also 10 and 35 ml pressurized vessels. So that's this vessel here is a 35, and here's your 10 ml. These actually feature very simple to use snap-on caps, so no tools are required to actually put those caps on the system. So you might be wondering right now though, how do I decide which is the right microwave system for me to use for my laboratory, my particular applications? So I kind of wanted to do a quick run through some of the differences between the systems. So in a Mars system, when you have a laboratory where you're going to be running more than about 10 students, you're going to want to use probably the Mars system. And again, this is the parallel synthesizer, the parallel synthesis system, so it allows you to run up to those 24 vessels. So it allows you to run those larger laboratories still very quickly. If you have a small class size, say you have less than 10 students, and especially if they're running in pairs, for example, then you might want to think about the Discover SP, because even though it's one reaction at a time, these reaction times are so very quick that the students usually can get them done, and they're usually staggered as it is because some students work faster than others. Now, in terms of your interest, if you're mostly just interested in the teaching labs, you don't really want to do much in terms of research, the Mars is definitely a better way to go as well, and again, combined with the fact if you have large class sizes. But if you want to do research and you're looking to do multitask with your system, the Discover might be a better idea because, again, you can run smaller samples on an individual reaction scale for doing some of your research chemistries in addition to the teaching. If you want to do large-scale research, so I showed you before the large setup with a large round-bottom flask, certainly the Mars is a better option for that. If you have limited bench space, the Discover SP is a much better system for that as well because it's a more compact system than the Mars unit. And certainly if you're mostly going to be teaching entry-level classes, and again this kind of goes hand in hand with class size, the Mars system will probably be a better option there. If you're interested in the microwave system more for your advanced labs, then Discover SP is probably a better option there. Again, you'll probably have smaller class sizes, and in advanced labs you often have the option where students can kind of walk up or sign up for systems, and they work outside of maybe the standard laboratory time periods. So there are some other tools available to you as well. One of those is a lab manual. So several years ago at this point, we, in collaboration with Professor Nick Leadbeater from the University of Connecticut and Professor Cynthia McGowan at Merrimack College, worked to publish this an organic teaching manual, and it's titled Clean, Fast Organic Chemistry Microwave-Assisted Laboratory Experiments. So you can see here, here's a kind of a picture of the cover, but this book basically was the first dedicated lab manual for doing teaching in the organic synthesis labs, and the entire manual is dedicated toward microwave teaching, so microwave experiments. So here just to show you a little bit more information about the book, what's included in there. So the first couple of chapters are some background information, some of the microwave theory, introduction to microwave technology, things like that, what has been done with microwaves and where it's going in the future. And then from there, it features 11 different experiments. So you can see here 7 independent experiments, and then there's a series down here at the bottom of a multi-step synthesis. Now you'll notice that many of these reactions are chemistries that you currently are running in your laboratories right now. And you can see that they're easily modified and adapted to run in the microwave system. But you also might be looking at some of these and thinking to yourself, well, I would never be able to do that in my classic lab right now because it's just an experiment that would take far too long. And that's what I was talking about earlier, how this will open up opportunities to teach chemistries that you wouldn't normally be able to do in your teaching laboratories. So I just want to take a few minutes and show you some of the chemistries out of this lab manual and give you some of the information about these chemistries and the background information. So the first one I want to talk to you about is this Diels-Alder reaction. So in the Diels-Alder, basically taking dimethylbutadiene and maleimide to do the cycloaddition reaction. So under conventional conditions, this reaction classically would be done in DMF for about an hour and a half at reflux. Then the workup would require extraction and then likely chromatography to clean up the final product. In the microwave, the way they were able to optimize the conditions is that basically the solvent was removed altogether. So this reaction is now run neat with an excess of the diene and only 10 minutes at 70 degrees, and this reaction will proceed to completion. So because it's done neat, all that has to happen is the excess diene is evaporated, and then the students are on their way to running the, basically continuing to do, say, the analysis or whatever it is that they're going to do. This reaction also works with dimethyl fumarate in addition to the maleimide. So another option is the esterification. This is your classic Fischer esterification, where you take acetic acid and an alcohol in the presence of sulfuric acid to form the ester. So conventional conditions, it's run neat, but classically it takes about an hour at reflux, whereas in the microwave it's only 10 minutes at 125 degrees Celsius. And the nice thing about this experiment is it gives students the opportunity to explore different substrates, and the students can either choose the different substrates that they're going to be using, or perhaps they can be assigned unknowns, and in the end they can try and figure out what particular product they had formed. And the nice thing about this experiment is it forms these esters that all smell quite nice, which is nice for the students, again, for learning about the chemistry but keeping it interesting. The nucleophilic aromatic substitution reaction, again, this is a nice example where there's multiple different substrates the students can be running. And so basically this is done with the bromodinitrobenzene and 3 different substrates. And so you can see here, conventionally, this reaction is done in toluene, and depending on the substrate, it'll take from an hour to an hour and a half at reflux. And of course, then the workup is extraction and then recrystallization of the product. The microwave method is done either in ethanol or ethanol water mixture, depending on the nucleophile selected. And the reaction takes 7 minutes at 125 degrees. So again, you go from an hour and a half to only 7 minutes. So if a student were to make a mistake when setting up this reaction, they very easily could go back and rerun this experiment, whereas typically with an hour and a half of reflux, they don't have time to go back and redo that. Now the nice thing about this experiment, because they've changed the solvent from toluene to ethanol or ethanol water, as soon as the reaction cools down, the products actually precipitate. And so all they have to do is cool it down, filter, and isolate the product. And it's also kind of neat because the products in this particular SNAR are very brightly colored. So again, kind of keeps the students interested and engaged because it's something visually stimulating in this particular case. All right, so I wanted to show you a little bit about this multi-step sequence. I didn't really go into it in much detail when I showed you the table of contents. So the way this process works, basically taking benzaldehyde and going through a process to take it all the way through to synthesis to form stilbene. So the way this works is the first step is doing a Novanagel condensation reaction and to form the transdynamic acid. And so in the Mars system, we actually run this in an open vessel because you'll note that it actually generates a pretty significant amount of CO2 in this reaction mixture. So again, taking advantage of the fact that you can actually run these chemistries in open vessel format. On the Discover SP, because of the Activent technology, you actually can still run this pressurized because it can very easily control the excess pressure. So with the transdynamic acid, then they can perform a bromination reaction with pyridinium tribromide. And from there, they can then do an elimination reaction. And again, this will then give them the bromostyrene product, and they can actually choose the particular solvent in this particular case to actually generate the E or the Z product depending on the solvent conditions selected. And then from there, a Suzuki coupling reaction with phenylboronic acid gives the stilbene. Now the nice thing about this whole series is that each of the individual starting materials are actually commercially available. So say for example, all you really want to do is show your students the elimination reaction, or you don't have time to run the whole series of experiments, you could run just the elimination, just the Suzuki coupling, any steps that you decide to choose. This is a nice appeal of this particular series of reactions. So I just wanted to quickly touch a little closer on this elimination. I mentioned the fact that you can actually, through solvent selection, direct the E1 versus E2 selectivity. And so based on this, basically they're choosing acetone as the solvent, so running from anywhere of 115 to 125 degrees in just 5 minutes. Basically the reaction will go through an E2 mechanism favoring the Z isomer. And then if you choose water as the solvent, anywhere from 100 degrees to 150 degrees, again 5 minutes, will go through an E1 mechanism favoring the E isomer. So again, it can kind of give you an opportunity to teach your students about those two different mechanisms, and also teach them about the analyzing for those two different isomers. How would you determine that? Things like that. So again, very important and relevant information. All right, so those are some of the experiments that come out of that lab manual. I just want to take just a moment to tell you about a couple of different examples that are actually in the literature, some things that have been done by some other different professors. So in this example, this is from Iowa State. What they're looking at is soap versus biodiesel production. So starting with a variety of different plant oils, olive oil for example, using different reaction conditions, they can direct either the saponification reaction, which I've shown here, which conventionally they run for 30 minutes at 115 degrees. And in the microwave it's 13 minutes, so basically 3 minutes at 140 degrees and then 10 minutes at 115 degrees. So it's less than half the time to run the saponification, or by simply changing the conditions from using water as the nucleophile to using methanol or ethanol, they can drive then the transesterification reaction. So conventionally it would be an hour at reflux, and in the microwave it's 8 minutes at 50 degrees Celsius. And so again, giving the students an opportunity to really quickly get these different reaction results, and perhaps being able to actually run both types of reactions, where maybe classically they wouldn't be able to get to both experiments in a single laboratory session. And just another example then from the literature, and again this is some variations on a theme of some of the experiments shown in the lab manual by Nick and Cynthia. So here this is some work from Muhlenberg College, and so here is another example of a Diels-Alder reaction that conventionally is an hour and a half at reflux, giving pretty good yields, good student yields for the cycloaddition product. But in the microwave it's only 10 minutes at 130 degrees, and you see no loss in yield here for the students in that particular reaction. In the second example here, this is a Wittig reaction, conventionally again an hour and a half at reflux. Here you can see about moderate yields for this particular reaction conventionally. In the microwave it's done in only 15 minutes, 200 degrees Celsius. And you can see again a nice increase in the yields for this particular Wittig reaction. And then lastly, this is a Williamson ether synthesis. Conventionally it's an hour and a half at reflux, and again low yields in this for the conventional reaction. And in the microwave it's 10 minutes at 130 degrees, and again you can see here we get a nice increase in the yields for the students. Now one of the things that you could always think about too, if you're interested in incorporating the microwave into your lab, but you're concerned because you want your students to learn these classical techniques, is you could always take these experiments, say half the lab run the conventional method and half run the microwave method, and then the next experiment you have them switch, so they get to still learn those classical techniques, but then also get the advantage of the microwave. All right, so expanding the scope of this technology, this is something that we wanted to do here at CEM, is find ways to go beyond the current lab manual that's available and go beyond the current methods that we have on hand. And really the idea here is to take this to general chemistry, inorganic and analytical chemistry labs. And one of the reasons we wanted to do this is that the microwave system really is a multifunctional system. It can do lots of different types of chemistry. It's not just good for organic chemistry reactions, it's also very good for lots of different types of things, from like sample preparation, for example, for doing trace metal analysis. That acid digestion technique normally is a very long process, but the microwave does a great job of accelerating that. So we wanted to look at expanding the scope of these experiments. And certainly what we're trying to do here is help you as a professor for adding justification for the purchase. So certainly in today's economy, when funding is limited and it's very difficult to get money for capital purchases, if you can have additional justifications for how you could use that system, we know that can help. So that's another motivation here. So one of the things that we wanted to do was first look at a general chemistry experiment, and really what we wanted to do is start at the very beginning, introducing microwave heating to the students, giving them some experiments so they can understand the mechanisms by which microwave is heating, and introducing these concepts of dipole rotation and ionic conduction that I talked about earlier. And so kind of giving them an idea of the different ways you could explore this in actually a laboratory setting. And what the goal here is then for the students is just to get very basic chemical concepts. I mean, these are simple experiments that we're talking about doing here, and also will help the students get familiar with the systems, get familiar with using the instrumentation, have them run in something that's pretty simple, not much that they can that they need to be concerned with in terms of like running a synthesis, for example. So simple lab techniques that they'll have to do. And it's just basically simple comparisons of heating rates and then also power consumption for the different materials that they're heating. And also looking at the microwave absorbing characteristics of different samples. Again, to understand these concepts of dipole rotation and ionic conduction. So here's just a couple of just some graphs that we've generated from this experiment, this general chemistry experiment that we've done. So here, if you're comparing the heating rates for different samples, we have these plotted. This is just basically, we did a fixed power method where we're heating for 30 seconds, and we're measuring the temperature that the sample could get to. And so you can imagine, so we have hexanes, which is a very low absorbing solvent. You can imagine the hexanes didn't get very hot. It only made it to about 30 degrees in 30 seconds. Ethanol, though, which we know will absorb microwave energy quite readily, it's a very high absorbing solvent, made it to basically 140 degrees in those 30 seconds. And so then we also took some mixtures where we took our hexanes and we added something to it, either be it either a heterogeneous mixture or a homogeneous mixture, and then also looking at something that would have a dipole and then something that would have perhaps ionic properties. And so here you can see the mixture with benzaldehyde heats much faster than just neat hexanes, and the same thing if we added iron oxide to the hexanes. So again, looking at the impact of all these different additives. We then also looked at the power profiles comparing a deionized water sample and a salt solution. And so here you can see now we're looking at how much power is being applied to heat up to a particular temperature. And so this is run over 1.5 minutes, and you can see to get up to our temperature with the deionized water solution, they both start very similar profile, but then you can see that in order to get to temperature in the amount of time that we're trying to do this, it needed to add more and more power to get up to the desired temperature. Whereas the saltwater solution, because of the presence of those ions, which are going to readily absorb the microwave energy, you can see only low amounts of power were required to get up to temperature. Now that has been written up in a full experiment that we actually now have available. So where can you find more information? Well, one place that you can do is visit our website. On our website at cem.com, we actually have a microwave university. And our microwave university is full of application notes and reference lists, information on our grant program, and there's also a forum there for having a live discussion with other users of the technology. And then also, CEM has published many years ago a very good introductory book to microwave synthesis, and this is called Microwave Synthesis Chemistry at the Speed of Light. And again, this is a good introductory book to microwave chemistry. Now, I did want to let you know that there's actually a new teaching manual available. So Professors Leadbeater and McGowan came together and wanted to expand upon those already existing 11 experiments that were kind of organic chemistry focused, and they wanted to take this and add inorganic and analytical chemistry experiments. So here you can see, here's actually the cover of the book. This just came out about a month ago. And then you can see they've got some of the similar reactions that you've seen before, the cycloaddition reactions, esterification, also included a biodiesel application. And then you can see there's coordination chemistry, organometallic chemistry, and then even some analytical methods, so extraction and digestion. So lots of different experiments here, 22 different available. So as another tool that's available to you for your teaching labs. So if you're pretty excited about everything you've heard so far, you might be wondering, well, how do I start? How do I take something that I'm currently doing and put this into my laboratory? How do I get started and know where to begin with my teaching laboratories? So what I would suggest is pick a couple of your reactions that you're running that currently take a long time, maybe an hour hour and a half. Those are really good reactions to try and cut down the time and make them be a little bit shorter using the microwave technology. Or select some chemistries that perhaps are newer and more relevant or more interesting chemistries, but they're far too long to run in your classical teaching lab because of the time limitation of your 2 or 3 or maybe even 4-hour laboratory periods. Look at some of that chemistry. But certainly the big thing is to stick with things that they need to learn, but try and make it more interesting by incorporating the microwave technology, or again, introduce them to chemistries that they wouldn't normally be able to do in their classical laboratories. Okay, so just to kind of sum up some of the things that I told you about, our goal is to get you to realize that the students need to know about microwave technology, so it's important to incorporate it into their curriculum as soon as possible, either be in the laboratory, but most definitely in the lecture at the very least. And certainly what it allows you to do by incorporating the microwave technology into your laboratories is you can decrease the amount of time it takes to run the reactions. You can explore more efficient reactions. Perhaps you could even go through this exercise of helping the students think about how you would make a reaction more green and get them thinking about improving and optimizing these processes. And lastly, I just want to point out that again, these scientific microwaves or these laboratory grade systems, they're a safe way to incorporate this kind of technology into your laboratories. The systems all feature temperature, pressure, and power control, and they're designed with safety in mind to protect you and to protect the students, of course. So first I would just like to acknowledge Professors McGowan and Leadbeater for the work that they did on the Clean, Fast Organic Chemistry Lab Manual. Certainly that was pivotal work that they did, and we really appreciate all their efforts. And then I'd like to just acknowledge my colleagues here at CEM for their continued work in supporting these projects. So lastly, I'd like to thank you all for your attention, and I'd be happy to entertain some questions.
Thanks, Grace. Microwave energy really opens up a number of possibilities for teaching synthetic chemistry.
Yes, it certainly does.
We all know that if you put, if say you're making a cup of tea and you accidentally leave the metal teaspoon in the cup and you put the cup in the microwave, that it'll arc. Can you use metal substrates in solution in a CM microwave?
Yes. And you say a very key important thing there is in solution. And actually it's not really in solution, they must be covered by solvent. But metals can readily be used in the microwave system. You just want to make sure that they're covered by solvent. So even if it's a heterogeneous catalysis reaction you're doing, as long as it's covered by solvent, you should be all set to go.
Are there any instances where you would use water as the solvent?
Yeah, actually, there's in the lab manual I mentioned, there's actually some nice examples where water was used as a solvent for example, the Suzuki reaction. Water can be used. So there's a lot of really nice examples where water can be used for microwave chemistry.
Can you happen to perform any solution-free solid-state reactions?
You can. There's a couple of considerations that you need to think about. The big thing there is mixing and agitation. Now, one of the nice things about the microwave systems that CEM offers is that they can be run in an open vessel format. And so to run those chemistries, what I suggest is using a mechanical stirring technique. And what you're going to want to do is through the open vessel, be able to use a mechanical stirrer to help agitate the sample. Now, the thing to keep in mind there is, again, if you have metal substrates, those are not going to be well suited for that type of chemistry.
Well, now, if you do have metal substrates, will they reflect the microwave energy?
Well, they have the potential to arc. They won't always arc. You have to have essentially the right conditions in order to form an arc in the microwave. So it's not guaranteed that it will arc, but again, it's just something to be mindful of.
Well, in that respect, is there anything that you shouldn't put in the microwave?
Well, what we always tell people is to use your common sense. You know your chemistry, and so anything that you'd be concerned about conventionally, you should be concerned with in a microwave. So, for example, if you have a reaction that you know is exothermic conventionally, it's going to be exothermic in the microwave, just probably a heck of a lot faster. So just keep that in mind when you're running the microwave reactions. Things you also should think about is you want to avoid high concentrations of very strong acids and very strong bases, specifically bases, and specifically in some of the vessels that I've talked about today, and namely because they're often not compatible with the glass vessels. Like high concentrations of bases, for example, will rapidly attack the vessels, and they heat very quickly, so it's just you have to be a little bit careful about that.
Now you talked about a number of different chemistries today in your presentation that you can do in a microwave. Can you do nanoparticle synthesis?
Yes, that's actually a great example of some chemistry that can be done in the microwave. And what's interesting is that in using the microwaves, you can actually adjust the amount of power being applied to the sample that can help actually impact the size of the particles that are generated. There's a lot of really nice examples in the literature where people have done nanoparticle synthesis using a microwave system.
What about temperature-sensitive reactions? Won't they overheat?
Well, okay, it depends on how temperature sensitive we're talking. So the nice thing about these systems, and again as compared to a conventional system, is they all have temperature control. And so if you say I want to run the reaction up to 70 degrees, the system will actually modify how much power is being applied to keep it at 70 degrees. Now say for example you're running a chemistry that if you run it above, say, even room temperature, it starts to decompose or something like that, then what you're going to want to do, and even conventionally you probably do this, is you want to run it at lower temperature. And there's actually a way to do that in the microwave system. There's basically an accessory that you can use with the Discover SP that allows you to actually run reactions below room temperature or even at room temperature. That accessory is called a CoolMate, and it's a very easy way to run some chemistries that might be temperature sensitive but might be able to take advantage of the microwave energy to accelerate the reaction.
How low can the CoolMate go in temperature?
The CoolMate itself, you can run reactions down to about minus 80 degrees Celsius.
Wow, that gives you quite a range.
Yes, it does.
Some schools have older microwave systems that they originally used for research. Can those be repurposed for teaching?
Yeah, you certainly can do that. Some of the things you want to look at is figure out what kind of vessels you have available to you, and then also I would recommend talking to someone from CEM to make sure that your system's in good operating condition and that the vessels are going to be suitable for the types of reactions that you're going to be doing. Oftentimes, say if you have one of our older style Mars systems, I showed you the Mars 6, if you had a Mars 5 that had maybe some different older framed vessels, all you would have to do is simply add the glass chem vessels to your system, and then you should be able to run some of those chemistries. So yeah, you absolutely can take some of the older systems that we've designed.
Speaking of glass chem vessels, what are they made of?
The glass chem vessels are actually made out of Pyrex. All of the actual glass vessels that we have are Pyrex vessels.
Are they reusable?
Yes. You can reuse the glass chem vessels basically until you see signs of any sort of failure, and typically that would be often due to somebody dropping a vessel and actually cracking it, but they can be used again and again.
Well, what if someone's running a chemistry that's not compatible with Pyrex? Are there other vessels available?
Yes, so even now the Mars system comes with a variety of different vessels. The Mars system, I mentioned how our systems are multifunctional. The Mars unit is a perfect example. It's actually can do many different types of chemistries. So there actually are vessel sets that are made, the vessel itself is made out of Teflon rather than out of a glass. And there's also vessels that have quartz liner, for example. So if Teflon's not something you could use and quartz may be a better option, you certainly can do that as well. So there's a lot of options available.
Oh, good. What is the lowest volume you can run in a Discover system?
In the Discover, you can run as low as a quarter mil, 0.25 milliliters.
And while we're mentioning Discover, it's not uncommon for professors to share equipment, and since the Discover is so much smaller than the Mars, is it possible to move it from one lab to another?
You absolutely can move it from one to the other. That's certainly a possibility, and you're correct, because one of the reasons is they do share the system. So yep, it's very easy to move it. We have many people who do that.
And a number of these reactions you were talking about today, you mentioned that stirring is important to some of them. What kind of stir bars are available for use?
You can use your standard Teflon-coated stir bars. We do suggest using the Teflon-coated stir bars, but that's about what most everyone has in their laboratories.
Oh, okay. Well, that's all the questions we have for today. We'd like to thank everyone for joining us, and we'd like to remind you that if you have any questions about today's presentation, please feel free to contact Grace or visit us online at www.cem.com. Thank you and have a great day.